Hello, everyone, and welcome to the 44th Surface Ventures keynote webinar. Please say hi in the chat and tell us where you're joining from. It's always great to see and hear where you're all from, and just to make sure that we're coming through loud and clear. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface and material science education for academia and industry. Today, it's my pleasure to introduce Dr. Amir Kadirik of the Tribology Group at Imperial College London. Dr. Kadirik is an academic in the Department of Mechanical Engineering at Imperial College London and a member of the Tribology Group. He leads the SKF University Technology Centre for Tribology at Imperial and chairs the executive committee of the Vehicle Futures Hub. His research interests include surface damage mechanisms, efficiency and reliability of EV transmissions, condition monitoring, and contact mechanics. Many thanks to today's partner, PCS Instruments. We will have a short presentation from Alexander McLaren later in the event, and we'll also be joined by other members of the PCS team. We have Ben Wainwright here with us today, and Kieran Nair, who will be making appearances on stage later if required. So be sure to say hello to them. And we'll be releasing poll questions from PCS and handouts throughout the event. We'll begin with poll questions and then proceed with handouts, and I'll give an indication in the chat when they will be released. As we go along, please type your questions into the chat and they'll be marked for the Q&A session later in the event. We're planning to go for around 60 minutes in total today. We'll be sharing a link for your attendance certificates later in the event. So without further ado, let's welcome our speaker onto the stage and take it away. Welcome, Amir. Good to see you. Getting the screen share set up, everyone. So there we go. See your screen. The slides up there, Amir. Not quite yet. There we go. Slides are up. Thank you very much. Take it away.
Thank you very much for that introduction, Sam. Thank you all for joining this webinar. Good morning, good afternoon, or good evening to you, depending where you are in the world. So I'm Amir Kadirik, and I'm going to be talking about some recent work we've done on using tribology to analyze and improve the efficiency of electric vehicle drivetrains. Now, I think the first thing I should say here is that the work I'll present contains results and analysis from a number of PhD and postdoctoral research projects. So I'd like to just give credit to a couple of my ex-PhD students, Joseph Shaw, who is now a postdoc working with me, and Alexander McLaren, who is now at PCS. You'll have an opportunity to see him later on this webinar. There's other work from other people, but I think it's mainly from Joe and Alex. Also, a word of warning, I am sitting in my office in Imperial in central London, despite that blue sky you see behind me, which means that I could be interrupted by any random students knocking on my door. So if you hear any knocking, please ignore it, and hopefully there'll be no emergencies. So let's start. So first of all, why are we looking at the losses and efficiency of a drivetrain electric vehicle? So I'd just like to do a quick comparison between a drivetrain of an internal combustion engine vehicle on the left-hand side here, and that of the electric vehicle passenger car we will be focusing on in terms of the losses in the drivetrain. So if we start with an ICE passenger car, you have the fuel energy. I'm not talking about where the energy is coming from. I'm talking about the energy on the vehicle. In the case of passenger vehicle powered by internal combustion engine, that's fuel, 100% fuel energy. And a lot of that, about 3/4, is lost in an engine through cooling, exhaust, engine friction, and so on. You can't do very much about that loss because the efficiency of an ICE engine is limited. So that means that only about 27, 25%, whatever, goes into the gearbox. From that, about 5%, thereabouts, those numbers can go up and down, but roughly about 5% is lost in the transmission of the gearbox itself. So the useful power driving the wheels is roughly about 22% of that fuel energy in the tank. Now, you probably know those numbers, but the interesting thing here is that if I just look at the numbers in red here, and I'll try to take the laser pointer. So if I add 75 and 5 and I divide 5 by that, it's only about 6% of the overall loss of energy is due to the losses in the drivetrain. If I do the same analysis for electric vehicles and I start with 100% energy in the battery, because the electric motor controller are very efficient, charging and discharging process is relatively efficient. There are some losses there. Overall, only about 15% of that energy is lost. So 85% now reaches the gearbox, as opposed to 27% or 25% in the ICE car. If we assume that the efficiency of electric vehicle gearbox and that of internal combustion engine vehicle are similar, so I'm going to say 5% is lost. You could argue that's not quite right, but let's say it is. That means that you have 80% of battery energy available to drive the wheels. That's a big difference, right? 22% versus 80%. But to us, the more interesting number is the ratio of this 5 over the overall losses, so 20%. That means that up to a quarter of the overall loss is due to the drivetrain losses in an electric vehicle. So clearly, one way to optimize the efficiency of an electric vehicle and hence extend its range, or for a given range, reduce the size of the battery, is to optimize the drivetrain efficiency. And this is really the motivation behind it. We had worked, of course, on improving the drivetrain efficiency of internal combustion engine vehicle, but now we can make a much bigger impact. Those numbers, of course, can go up and down depending on the duty vehicle and depending on which papers you read. So I'm just giving you an overall picture here. The picture certainly will not change if those numbers are changed up to a point. Now, I'm sure most people online are familiar with the architecture of electric vehicle drivetrain, but just to tell you which part of this architecture we are going to be considering for the rest of this talk, I've got this very simple picture here that shows an electric vehicle, top left, and of course it has some batteries, it has some power electronics, the electric motor, and the gearbox. Now, these three bits are usually combined into something called electric drive unit. A picture of a real electric drive unit is shown down here. It's relatively small, much smaller than internal combustion engine and a transmission in an internal combustion engine power vehicle. And if you open this up and you look inside, you see what's shown on the right-hand side. So I'll just go through it briefly. So here we have a motor, electric motor. So we have the rotor shaft and the stator. And then we have some transmission bolted onto it. The transmission is usually, not always, but usually, two-stage single ratio transmission. So what we have is the input stage here, the input pinion, the intermediate shaft with the wheel and the pinion, and then we have the output stage wheel here. Then you have some differential, and this drives the wheels. Each of those three shafts is supported by bearings. In this particular vehicle, there are 7 of them because there's an extra bearing here. And in addition, you have some oil filters and heat exchangers to cool the oil. The pink color here is meant to indicate the oil, or what we often refer to as e-fluid. It's basically the electric drive unit lubricant. In the particular example I'm showing you here, I'm trying to illustrate the fact that the same fluid is used to lubricate the gearbox on the right-hand side here and cool the motor on the left-hand side here. Hence, I've got the same color everywhere. Of course, there'll be certain immersion depth and so on of the gearbox and so on, but the color is just to show you that the same fluid covers both of those. And that actually is an important consideration in terms of tribological challenges presented by an electric drive unit when it comes to optimizing this e-fluid. And you can see what happens with the oil flow. So if I start with the oil flow coming out of the gearbox, it'll go through some filter, it will go through a heat exchanger, it will get cooled by some cooling fluid here, and then part of it will go to cool the motor, and then that will then enter the gearbox, and another part will bypass the motor and will be sprayed onto the first stage and then be collected in the sump. So even though it's sprayed, there is actually certain immersion depth of this first stage, and then the second stage is purely lubricated by these gears being immersed in a sump. So there's some jet lubrication elements of the first stage and dip lubrication for the second stage. So throughout this talk, we'll be considering this system on the right-hand side, but I think it's important to say that there are alternatives to this. This is by far the most typical one used in current electric vehicles. If you have a light-duty commercial vehicle and even some sports electric vehicles may have multiple ratios. In this particular case, we have a single ratio transmission. So what we want to do is optimize this fluid. We also are working in the Department of Mechanical Engineering. So we're also interested in optimizing the actual architecture of this. But today I'll be talking mainly about optimizing the properties of this fluid in terms of efficiency. So what are the challenges? So I've got a list here, and I apologize that this slide is quite wordy, but hopefully you can read it for yourself. The main point really to take away is that this e-fluid is subjected to competing challenges. So you need to, the electric vehicle drive units operate at quite high speeds, and this is because you want to run the motor at high speeds, reduce the size of the rotor, so I have the same power and so on and so on. There are some very good arguments why you would like to run that motor at very high speeds. What that means is that you're churning a lot of oil and the bearings are going high speed, gears are going at high speeds and so on. If you want to reduce losses at those speeds, generally the accepted wisdom, which may or may not always be true, is that you need a low oil viscosity. Now, on the other extreme, when you have very low speed or you're just moving off with an electric vehicle, you're producing a high torque just due to the torque speed characteristic of an electric motor. Now, to protect the surfaces under those conditions where you cannot rely on a thick enough hydrodynamic film, you really need a higher oil viscosity. You need specific formulation of an oil to protect the surfaces in boundary and mixed lubrication. So you have an issue here because on the one extreme you need low oil viscosity, on the other extreme you want high oil viscosity. It doesn't stop there, unfortunately. If you are using the same fluid to cool the motor, to lubricate the gearbox, you have to think about copper compatibility. So the sulfur additives can be an issue in that case. But these gears can also scuff. Scuffing is one of the most common gear failure modes. And if you have high loads, high speeds, scuffing becomes more likely. So sulfur helps in that respect. So you have this competing requirement of, do you put sulfur, do you remove sulfur, high viscosity, low viscosity? Where is the optimal? Clearly, you can't satisfy all of those at the same time. And that's an important message to take away. The e-fluid properties do have to have a compromise to address these system level competing challenges. They're not necessarily the best solution for any one of those challenges, which is a bad thing, but also in a good thing in a way, because it does open up possibility of using some unconventional fluids in these units, as we will discuss a little bit later. You also need to cool the motor, so that also requires usually a low oil viscosity as well as high heat capacity and so on. And finally, while considering efficiency, we mustn't forget that we also have to ensure at least keep the same level of reliability. So we need to resist certain damage modes that I talked about, scuffing. And of course, you can have other standard damage modes for gears and bearings, pitting, micro pitting, and so on. But in electric vehicle drive units, there's some specific damage mode that's due to the electric potentials, and that's another area we are studying. I will talk on a little bit in this talk because the talk focuses on efficiency. But whatever e-fluid you choose has to deal with reliability. So it's a little bit of a mess. It's a fast-moving area. There's a huge amount of research in this because you can imagine all of a sudden we have these different requirements and we can't use the fluids that we've been using for hundreds of years in thermal combustion engine. So there's an opportunity there for somebody to come up with a fantastic fluid that can do all of these things, but it's also a challenge. And to aid those challenges, we do need some new tools in order to allow us to find out what is this balance between these competing requirements on the system level. And what we are trying to do, and what I'll show you today, is how we're using tribology to try to find this optimum compromise by considering the whole system. So what are the main tribological challenges in doing so? I've listed three here. There are many others, but I think those three are quite important, kind of ranked. The first one is the high speeds. Unfortunately, the speeds encountered in electric drive units are higher than most current tribometers have been designed to deal with, which means that if you are testing frictional wear properties of particular fluids, we can't reach the speeds that these electric drive units, the gears and bearings in the electric drive units operate at. So we need to think a little bit about how to address that, and I'll show you what we've done in that respect. We are getting there. There are some new test rigs that allow us to do that better. Number two, well, we are tribologists, so, you know, if you go to a store and you buy oils that have the same specifications, we like to think that we can tell a difference between them. Otherwise, we're wasting our time because they're not the same in terms of friction, in terms of wear. Now, if you want to distinguish between two same specification oils in terms of the impact on overall losses on an electric vehicle while it's being driven through London, it does require a quite detailed analysis from a tribological point of view, where those losses come from. And crucially, absolutely crucially, it requires measurements to characterize those fluids. So even though the specs are the same, they certainly have differences in terms of overall EV efficiency, as you will see later. Number 3, arguably, is the most important one here. Losses in electric vehicle drive units come from different sources. They come from gears, come from bearings, they come from churning of the oil as the gears are rotating, as well as bearings are rotating and so on. Those losses interact, and I'll show you that on the next slide. The way they interact is usually through temperature, through heat transfer response of the transmission. So what that means is that if you are trying to assess impact of particular e-fluid on bearing losses, gear losses, or churning, because of these competing challenges, because of interaction between them, you really need to consider the whole system. Because by improving, say, gear losses, you may make the bearing losses worse, and overall your EV efficiency may not change or may be worse. So the system level approach is important. Now, the crucial part of the system level approach is the evolution of temperature of an electric drive unit as the vehicle is driven through any duty cycle, be it a standard duty cycle, WLTP, or be it driven through middle of London or whatever. But you do have to consider all of those losses throughout the duty cycle, look how the temperature evolves, and then use the properties of this e-fluid at those temperatures in order to get the overall losses. And the idea is at the end to end up with a number of kilowatt hours energy loss, because for most manufacturers it's kilowatt hours the cost. That's equivalent to that dollars. So the number 3 is really the key requirement: system level tribological approach to predict the evolution of the EDU temperature and hence the interaction between these losses. This is why it's important. What I have here is an example from a simple gearbox. This is not from an electric drive unit. This is a simple one-to-one single stage gearbox that illustrates this thing. So as you have losses in bearings, gears, and churning, the oil temperature in the gearbox will change. It will increase. As that increases, it will change the oil properties, primarily the viscosity, as well as other properties. That means that the friction in the gear teeth contact, the drag losses in bearings, or the churning will change. So that means your power losses are now different. So you're pumping the different amount of oil in here. And now in a normal gearbox that's standing and operating at a steady state torque, steady state speed conditions, because it's driving a fan, say, this is quite a simple calculations, because you will reach an equilibrium temperature depending what the ambient conditions are, and you can calculate and then use those operating equilibrium temperatures to work out your oil properties and hence your losses. Unfortunately, in a moving vehicle, that's not the case, because the torque and speed going through this gearbox are changing non-stop. So the temperature of the gearbox is evolving. So what I have on the right-hand side is a simple gearbox where we started at 25 degrees, and then we've evolved the temperature as the gearbox is operating at 0.6 hours in this time. And in yellow are the total losses. So I've added all the gear losses, all the bearing losses, all the churning losses. But the bottom 2 curves are the interesting ones. What you see is the mesh loss in gears going up as the temperature has gone up. Bearing loss is going down. And the obvious reason in this particular case, which includes the roughness of gears, is that the lower viscosity caused by higher temperatures has caused higher losses in gears because they've been moved further into the mixed lubrication, gone up the Schreiber curve, if you like. Whereas bearing losses, we generally tend to be smoother than gears, like lower viscosity, so the losses in bearings have dropped. This needs to be accounted on a system level throughout the whole duty cycle if you are to optimize the e-fluid. And that's what we are trying to do with this tribological system level approach. So I'm going to consider gear teeth friction. I'll show you how we do this. I'm going to consider churning losses. I'll show you a little bit how we do this because it's different from the published sources. We recently published our own work on that. And I'll tell you how I do bearing and C losses. That is based on existing models, so we are working on improving that. But at the moment, we're using other people's existing models. And finally, I'll tell you how we combine them all into the system level approach. So first of all, gear teeth contact losses. So there's a little bit more tribology here than in the rest of this talk, for those of you interested in more technical detail. So we are using a relation between shear stress and shear rate for a fluid. In this case, I'm using a Johnson to Warwick relationship. You can plug in your own one if you don't like this one. It's a plug-in to the model. And what this does, it says, for these conditions, these shear rates for a fluid that's expressed with its viscosities and some of these constants to 0, I will get the shear rate. And then if this this shear stress. And this shear stress is higher than some critical shear stress. I'm having a limit of T is equal to 2C. This viscosity here is the viscosity of the oil at the temperature of the contact. So in the diagram here, we have the two surfaces. We have the oil in the middle here. The temperature here in the contact, indicated by this T oil here, red circle, is the temperature that we need to work out this viscosity. The shear rate here, gamma, which is shown in this equation on the right-hand side, is worked out by sliding speed divided by central film thickness. The central film thickness needs to be worked out or measured better at the temperature of the inlet. So you have these two temperatures that you need to work out for a gear teeth contact in order to work out a relation between shear stress and shear rate. Now, this requires an iterative model. We do use an existing glacier by Oliver and Spikes, two colleagues of mine, and also an update from postdoc of mine. Oh, I'm sorry, this is going itself, by Rices and myself, published in 2019, and also some COMSOL multiphysics input to work out a heat transfer coefficient. You can imagine this is quite a difficult calculation because your gear is operating in some complex mixture of air and oil. What is the heat transfer coefficient to work out how much heat is being lost from the gear, and hence gets the equilibrium between the heat being pumped in the contract and being lost to get a bulk 2 temperature, which is what we need in order to get this relation between shear stress and shear rate. Then we get our tau bar, and then we put in this relation. We divide the mean shear stress, tau bar, by the mean pressure to get the fluid friction. Now, this is very nice. It's fluid friction. Unfortunately, gears don't often operate in full fluid film, not in full EHL film, because they're rough. So we need to account for the boundary and mixed lubrication friction. And in our model, this is how we do it. We say the effective overall friction coefficient is equal to the fluid friction that we worked out using that relationship I showed you earlier, plus this term, which says it's boundary friction minus fluid friction divided by 1 plus lambda, lambda being the specific film thickness, the ratio of the film thickness to the surface roughness to some exponent n. Effectively, what this does is shown in this graph on the right, the bottom right. These are measurements for different surface roughnesses, friction coefficient on the x-axis, difference between smooth and rough. You can just consider it as a friction coefficient, and lambda ratio here. So this relationship effectively fits the friction between this boundary friction shown here, a low lambdas, to the fluid friction shown here, a high lambdas. I'm really sorry because this talk is actually doing going through itself. I can't stop it. So you can see that this term, as lambda increases, becomes 0. So our friction is just mu f. And as this lambda is very low, this becomes mu b minus mu f and mu f cancel. So we got mu b. So we're basically fitting between mu b and mu f. Works quite well. We do measurements for our fluid together. The other measurements we do for the fluid is to characterize the rheology of it. And the way we do that is we measure friction coefficients at different pressures, different temperatures, different slide roll ratios using our ball and disc turbometer, the PCS Instruments MTM. In this case, we actually use the scaled up version of MTM called ETM, Extreme Traction Measurement Machine, which is very similar, but it allows us to reach higher pressures. It actually allows you to reach up to 3 gigapascals for steel and steel contact. So it's a little bit more realistic in terms of conditions that may be experienced by bearings and gears in an electric drive unit. In parallel, we measure film thicknesses on optical EHD rig by PCS Instruments. And what that then allows us to do is plot a shear stress relationship, which is this mean shear stress, tau bar is equal to the friction coefficient times the mean pressure on the y-axis, and on the x-axis, we plot the shear rate. Gamma is equal to sliding speed divided by the central film thickness. We can then get this gradient of this curve to get our wiring stress, tau 0, and plot and get that relationship that I showed you in the beginning from this curve. On the right-hand side here, you have thermal effects, which you can, but you don't have to account for. And then we can plug our worked out mu f back into this equation, but we also measure the boundary friction coefficient mu b. Now, this is all very nice, and we've been doing this quite a few years now. I think this method was first done in 2001 and has been updated and so on and so on. But what you find is that because of the high speed conditions in electric drive unit, the normal turbometers that I showed you earlier don't really do that very well. So we've recently started using this high speed turbometer, which is similar as the normal EHD, but runs at 20 meters a second, to measure the film thicknesses and traction at speeds that are much more representative of real electric drive units. So here's a typical electric drive unit. Bearing entrainment speeds are up to 26 meters a second. Gear entrainment speeds are 18 meters a second. The previous tribometers only go up to 4 meters a second, but this new one does 20 meters a second. I'll show you some results from it. This is published work. We've got some film thickness and entrainment speeds, very high speeds, up to 20 meters a second. This is recently published, Alex McLaren's work. And you can see that the measured film thickness, which is those curves here, varies, deviates from the predicted film thickness, which is shown in orange here, as the speed increases. Interestingly, the deviation starts roughly at about 4 meters a second, which is the limit of the existing tribometers. So our current EHD theories don't predict this drop-off. There are compensating factors. Some of you might have used things like Gupta factor and so on. They don't really predict this very well. They're usually too conservative, but not always. On the right-hand side, this kind of indicates the level of this difference between the measurement and the prediction. This is the film thickness deviation percentages, slide-roll ratio, and entrainment speed. And you can see in some cases, for some oils, this is a PaO5 oil, you can get a massive difference, up to 40–50%. And in other cases, it's less, of course. This is the extremes, if you like. You can see up here, it's very low at low speeds. So we use this high-speed tribometer to get our friction and film thickness and plug into our model. Now, that's gear friction. Bearing friction, as I said at the beginning, we use an existing model. That's due to Guillermo Morales SPL at SKF. This is a published model. It's in the catalogs. They call it a four-source bearing friction model because it includes the rolling friction, sliding friction, the seal friction, and the drag losses in a bearing. So this is, if you like, equivalent to gear churning. So when I show you bearing losses later, that includes the bearing churning losses. And when I say churning losses, I'm referring only to gear churning losses. The original model was developed by SKF in 2006, and they are pains to tell the world not to use it if your NDM parameter, which is the bearing RPM speed times the mean diameter in millimeters, is over 500,000. And the reason that is because at higher speeds, this over-predicts the losses because the M drag is over-predicted. They have recently published an update to this model, which has got some factors to account for this. It's not physics-based, it's an empirical factor. So we've been using that model in our current predictions that I'll show you later. However, we've got quite a substantial amount of work trying to optimize those bearing friction predictions at higher speeds, including a new rig that we can run up to 45,000 RPM or 2.5 million NDM, so much higher than the current limit, so that we can apply these measurements and a better model into our EDU loss predictions. The gear churning losses is the third part of this overall system approach. And here we are relying on our own measurements. And the reason for this is that the current published gear churning models, which are empirical, are based on data that doesn't go high enough speeds. Usually about 7,000 RPM is the limit. We need to go higher because the speeds in electric drive units are, 15, 20,000 RPM. So we've done our own measurements, and the way we've done it, we have a simple plastic gear in this case, in this annulus, and we have a sump of oil here. We change the oil, we change the immersion limit, and so on. We get loads of measurements done for different oils, different immersions, different geometry of the teeth, and so on, different phase width of the gear, and so on. And then we produce our own regression equation. And we use that regression equation, which goes to much higher speeds, in our models. It comes up with some really interesting things. And I want to show you briefly what those are. The first one is this relationship between gear churning loss and oil viscosity. Now, conventional wisdom says that high viscosity gives you higher gear churning losses. And that is true within certain conditions, but it is definitely not true overall. What you see in this graph here is the measured churning torque from the rig I showed you earlier, plotted against viscosity of the test temperature on the x-axis. And these are different speed curves. So if you just focus on one speed, let's take the high speed, 3,500 RPM here, you see that initially as the viscosity increases, the churning loss drops. Indeed, it starts going up after a while, but initially it drops. So there's an optimum viscosity in terms of minimum churning losses. Now, that will be casing dependent. And you might wonder why that makes no sense. The more viscous oil is, the higher churning losses is. Not true. And other people have seen the exact same thing. And the reason this happens is this. What I have here is a series of images from that rig. And going from left to right, I have increasing speeds. And going from top to bottom, I've got increasing viscosity. So I've got PaO2, PaO6, and PaO40 oils. And what you see is this focus on this immersion depth here. This is the oil. We started in each case with each oil with the same immersion depth. This is 0 speed. As you run the gear higher and higher speed, the oil is being thrown up. Some of it comes back. So during the actual operation of the oil, there's a certain effective immersion depth. What that effective immersion depth is very much depending on the viscosity of the oil. So if you look at this effective immersion depth for low viscosity PaO2 oil and high speed is here. It's quite similar to the fill, the initial fill. If you look at the high viscosity oil, that was the initial fill, but look at it here. Your effective immersion depth is very, very small. It's almost 0. What that means is that you're actually going through smaller amount of oil, smaller depth of oil, and that reduces your churning losses. Now you might think, well, this is actually specific to this rig, and indeed the absolute values of churning loss are specific to this rig. But we actually did it in a real electric drive unit. So here's a real electric drive unit. I should say the way we do this is we spin up this gear to a certain speed, and then we disconnect it and let it slow down due to this churning loss, the drag of oil. And then from the speed time graph, we get a churning torque. So it's called inertia rundown method. And we did the same method here. This is work of Alexander McLaren during his PhD. We have an electric drive unit from a popular passenger electric vehicle connected to a motor. We spin it up. We disconnect it with the clutch, we'll let it slow down. And same method as the other rig. And indeed, what Alex has found is the exact same phenomena. So these are different speeds, so different vehicle speeds, different RPM. And let's focus on one of the speeds. So take this top one, 120 miles per hour, very fast. But you can see that initially the torque goes up with viscosity and then it drops. And then it goes up again. So it's not the same place in terms of viscosity, it's not the same speed and so on. But the fact that you see the drop, that generally the trends are the same. In the same gear unit, Alex also varied the immersion depth. And this is important because you find that the biggest effect on gear churning losses by far is the immersion depth, not the viscosity. So what you have here, compare either the red or the green curve. So let's look at the red curves. They are at the same speed of 88 miles per hour vehicle speed, 10,000 RPM gearbox speed. So you got 1 liter and 2 liter fill of the gearbox. 2 liters is really what it's filled with. And you can see this is the churning loss here for the 2 liter, and this is for the 1 liter. Big increase, double. So the effect of immersion depth is much more pronounced than the effect of viscosity. The trends we see in terms of churning loss versus viscosity are the same in both our lab rigs with single gear and a full electric drive unit. We then went off and applied this model to a popular current passenger electric vehicle. And this is the gearbox that I showed you in the beginning. Roughly 9:1 ratio, which is very typical of these transmission units. 300 Newton meters rated input torque. All of these bearings that you see, 7 bearings, are deep groove ball bearings. We are indeed having this wet motor design where a single fluid is lubricating both the gearbox and cooling the motor. We have a heat exchanger, basically the design I showed you before. And to address this temperature evolution and interaction of the losses, what we implemented is a thermal network model. So these numbers are the nodes of our thermal network. So we work out the losses at each of these points, bearings, gear meshes, and the churning, and the heat exchanges at each point, including in the motor, because of the cooling of the motor, in the heat exchanger, between the gears and so on. And then we allow them to talk to each other to get the overall evolution of temperature as the car is being driven. What Joe and Alex then did is drove that specific vehicle through this route, and the car was instrumented with lots of thermocouples in the transmission. We can't measure losses in an operating vehicle, but what we can do is measure the temperatures in different locations within this electric drive unit, and from there infer the power losses. So the higher the power losses, the higher the temperatures. We'll be inferring the power losses, but the relationship between power loss and temperature is pretty strong, so it's a good comparison. What I'm showing you on the right-hand side is the speed profile and the torque profile for this particular duty cycle that they drove the vehicle through. This is not a standardized duty cycle. This is a real-world duty cycle. We then put these speeds, these torques, through our model, and that characteristic of that vehicle, the electric drive unit, and this is what we got. So what I've got here is 5 comparisons for 5 of the nodes that I showed you here. So bearing 5 is here, node 12. And this is the comparison, and then we got bearing 6, heat exchanger, oil output. All of these are measured in blue and predicted in orange. So you can see that our model is pretty good at predicting temperatures within this electric drive unit for this particular lubricant this particular drive cycle throughout the gearbox. Frankly, I was actually a bit surprised at this. We have improved this over time, so these are the latest predictions. There are some differences in high speeds, and we have a rough idea why that's happening, so we're working on improving that further. But it's pretty good. So we're quite pleased with this in terms of validating our model. Having validated it, we then took that model and tried to analyze the efficiency of electric drive unit for different oils. So the first thing we did is took two oils, experimental fluids, not real commercial fluids. We call them oil A, oil B. Very similar, so these are the viscosities of 40 and 100 degrees, 29.4 and 5.9 centistokes versus 27.3 and 5.9. So roughly dextron 6 specs. It's an ATF. I've deleted some of the property fluids here because this is a recorded webinar. These are experimental fluids. Measured boundary friction coefficient is 0.118 and 0.13 for oil and oil B. So it's different chemistry, different additives. The base fluid is slightly different as well, but they satisfy the same specs. You could take one oil and replace the other oil in your gearbox, in electric drive unit, because they satisfy the same specs. This is what we got. So what I have now is a WLTP cycle, standardized cycle that manufacturers will publish their efficiency figures over. So I'm sure you've seen this. This is the vehicle speed on time for a standardized WLTP cycle. We run the vehicle through this cycle with these oils. Remember, we measure the properties of the oils, both the rheology and boundary friction coefficient. We're trying to tell the difference between them over the WLTP cycle. Here you have the evolution of temperature, this black line here, plotted on the right-hand side, and the individual losses. So in yellow, bearing loss, in orange, churning loss, and in blue, gear loss in an electric drive unit for that particular vehicle. And you can see how they evolve over time. You can see that the bearing losses dominate. At higher speeds, churning loss becomes significant. Gear losses as a proportion are less, but at lower speed, gear proportion are much bigger than at higher speed, and churning loss is smaller. And this is for oil B. You can't really tell the difference between oil and oil A and B here. However, if you add it all up, you remember what we are after is kilowatt hours, because kilowatt hours means dollars. So kilowatt hours energy loss, you find that oil A is about 2.5% better than oil B, largely because of this lower boundary friction coefficient and giving you lower overall gear losses. The other ones are quite similar. The biggest difference in gear losses, I remember gears operate to mixed lubrication, so it's the new B that made a difference. If you did a third formulation that reduced the bearing losses, you could probably do even better. But in this particular case, between these two oils, we were quite pleased to be able to see a difference, even though they're the same spec oil, so you could just swap them directly. What we did then is took some series of hypothetical oils and changed the viscosity. So we had lots of different viscosity, and I'm showing you figures here for oils of 2 centistokes, 9.2 centistokes, and 20 centistokes, 100 degrees. And again, we just run it through a WLTP cycle, and I'm showing you the same plots of bearing, churning, and gear losses in yellow, orange, and blue, respectively. What we've got on the right-hand side is a total loss. We've normalized it here, not to show the real numbers, and we've got kinematic viscosity here. What you can see here is, depending on your oil viscosity, the loss will change. You're not surprised, right? The interesting thing is there's an optimum. For the WLTP and that particular unit, it's around 3 centistokes. If you go any higher, what happens, you can't quite see here, but the bearing losses go up. Bearings like low viscosity oil, so it's not good. If you go higher this way, your gear losses go up. There's an effect on churning losses as well, but gear losses go up. So going down to some crazy low viscosities of 2 centistokes, 1 centistokes, is not going to help you. And that was quite an important result here. There is an optimum viscosity, which is relatively low for this particular cycle and this particular gearbox, but it isn't 0, it isn't 1 centistoke, it isn't 2 centistokes. There is an optimum that we can predict. However, this is specific to the gearbox, specific to the cycle. If I change the vehicle duty, which is what we did next, so this is the same results on the previous slide, standardized WLTP cycle, which is the one that they use to publish their efficiency figures. We took another standard cycle called Artemis. Some of you might have seen this. It's an urban cycle where you have more rapid changes in vehicle speed, more acceleration, more deceleration, and so on. What happens then, if you do exact same calculations, the optimum viscosity is different. All of a sudden, it's closer to 5.5, 6 centistokes, 100 degrees. If you drive your vehicle through London and I drive my vehicle through London, we probably need different viscosity in our cars because I'll drive differently from you. If you drive the vehicle in London, you drive the vehicle in, I don't know, in Yorkshire, you probably need different viscosities. We can't do all that, but it's an important finding, an important consideration that there isn't really an optimum viscosity for all duty cycles, for all transmission designs and so on. They will vary depending on what the vehicle is doing. And the important thing is also there is an optimum. We can change other properties. So one thing that we did is change the thermal conductivity of the oil. Remember at the beginning I said that the job of this oil is also to cool everything, including the motor. So there's a lot of research going on in terms of trying to increase the thermal conductivity or heat capacity of the oil in order to drop the temperature of the motor, because the idea is that the lower the motor temperature, the more efficient it is. We struggle to find published figures on the effect of temperature and efficiency of the motor. So what we've done in this particular model, we do include the heat exchanges in the motor and the efficiency of the motor, but it's at one single temperature and it's from published figures. We don't model it ourselves. But what we can predict is the effect on the temperature of the motor of change in the thermal conductivity of this oil. And you see that in this curve. So the stator temperature is shown in orange for different thermal conductivities, same viscosity. This is actually oil A, I showed you before. And the sump temperature here in blue. You can see as I increase the thermal conductivity, there's quite a big drop. In the motor stator temperature, I'm predicting at about 5 degrees drop. Now that sounds little, but it's a significant effect, I'm told, I haven't seen the figures, on the motor efficiency. We are working on getting those figures. So the higher the conductivity, it appears, the better. So why don't we use a high thermal conductivity, high thermal capacity fluid, such as water? And indeed, there are attempts to do that. Pure water is here, but of course you can't put water in a gearbox, but you could put some water-based lubricant, which will be taking you somewhere in this region, about 0.4 and so on. So water-based lubricants are being researched, including here at Imperial, in terms of the application for EDU. Not as good as oils at lubricating, but much better at cooling. So let's see where that compromise is. Caveat in this graph is, of course, as I said, we are not accounting for this reduced temperature of the motor on the motor efficiency. We're only using the motor efficiency at one temperature in our model. It's only to illustrate the hypothetical effect. Finally, what I just want to tell you is that it's all very nice optimizing these fluids to increase the efficiency. You mustn't forget reliability. And we are working on that in parallel. I don't have time to show you all of the work in terms of surface damage modes, micro-pitting and pitting that we are doing. And that's a major area of research in my group. What I want to show you is some work that's specific to electric vehicles, where we are looking at the damage caused by small electric potentials. So in an electric motor, electric drive unit, there's a source of electric potentials. There are stray currents, and people are finding that a certain damage apparently induced by presence of these voltages and currents. Now, we've known for decades that high current densities discharge of current destroys the surface. We understand this. What's interesting really is what the small voltages do. That hasn't been researched, and particularly what they do in mixed lubrication conditions for gears and bearings, not in full film where the discharge is the dominant mode. So what we have is a setup here where we apply voltage across the ball and disc contact, and this is the rig. We basically have the small MTM instrumented. It's MTM EC that allows us to control this voltage across the ball and disc contact, and also allows us to look at the development of the films. If you're interested in this, you'll have to read some other literature. But what we find that indeed application of very small voltages, 5 volts, affects, in this case, performance of ATF. We find that on the right-hand side, 0 volts means non-electrified, and then it's 5 volts, either as a cathode or anode, so we can swap the polarity here, affects the wear massively. When the particular lubricant formulation, ATF, is as a cathode, we get huge amounts of wear, quite a lot as an anode, but much less, and the smallest amount when it was non-electrified here. So in this case, it's an ATF, which is a formulation you could use in an electric vehicle. We're also monitoring the evolution of boundary film, and that is also affected by presence of voltages. But I'm not showing you ATF evolution here because it's not very obvious. I'm showing you ZADP containing oil. ZADP containing oils are not used in EVs. This is just to illustrate the potential effect. We have non-electrified 5 volts as a cathode and 5 volts as an anode bowl, and you can see that these colors indicate the development of boundary film, and indeed the anode is very different from cathode, and cathode is quite similar to non-electrified. So there are different effects going on here depending on formulation of the oil. It's really important to say that the effect on ZADP containing oil versus ATF containing oil is very, very different. There's an effect of polarity, there's an effect of voltage magnitude and current magnitude, but we are doing this in parallel to the efficiency work in order to tick both boxes, increasing efficiency, improving reliability. My final slide, in the interest of time, is this. It's all very nice predicting the losses over a whole WLTP, and this is really what we want to do in order to optimize the fluid and the transmission design, if you like, because those are the figures published. But to illustrate the effects of speed, it's much better to do this. Run the gearbox at a constant power input, in this case 15 kilowatts. So in this, the car would be doing a certain speed. But what we are doing is changing that speed, vehicle speed. But if we are changing the input speed, that means I'm fixing the power, that means we have to change the torque. So what you see here, from left to right, we're increasing the speed at fixed power. So we are decreasing the torque, shown at the top here, from left to right. And you see some very interesting effects. These colors here illustrate the losses from different parts of the gearbox. So in blue, we have first and second stage gears. In red and dark red, we have first and second stage gear churning, and the rest is all bearings. So first shaft bearing, second shaft bearing, and the output shaft bearings. What you see is a low speed, high torque condition. So you're just moving off, slow speed driving, lots of torque. The gear friction is dominant. It's 50% of the losses. As you increase the speed, the bearing losses become the dominant. The overall, they are here by far the most dominant. So bearings contribute by far the most, apart from our low speeds. The churning losses, again, almost nothing at low speeds, and then significantly higher at high speeds. I must say this bearing loss include the bearing churning losses. When I say churning losses here, I'm only referring to gear churning losses. So you can clearly see this evolution of losses with speed and torque. And overall, if you add this up, indeed, our model predicts 10 to 25%, depending on the speed torque conditions that the vehicle is operating at, of the overall loss is coming from this EDU, which is the numbers I started with. This is my summary. So what can Tribology do for EV drivetrain efficiency? I think I tried to illustrate the fact that designing these e-fluids and designing the architecture of the gearboxes as well, which I didn't talk about here, is a challenge. And there's a lot of new work on it. It's a fast-changing area. And we are trying to contribute to it by using Tribology on the system level to predict bearing, gear, churning losses together to predict the evolution of temperatures as you drive your vehicle in order to optimize that oil. Crucially, we don't just rely on modeling. We include the oil properties measured in our rigs so that we can tell the difference between two similar or same oils. And I've illustrated the fact that we can. And I think our results then show that there is indeed an optimum for any vehicle duty, and that optimum is dependent on that vehicle duty. So one for WLTP, one for harsher, one for less harsh cycle. But the nice thing is that there is an optimum. The low viscosity is not necessarily a good thing for churning losses. There appears to be no need to go to ultra low viscosities, and I think the world is slowly realizing that. And manipulating some of the other properties, I showed you conductivity, for example, can have a significant effect. And overall, gear friction significant at low speed, high torque conditions, bearing losses in the middle range and at high speeds, and gear churning only at high speed conditions. So the optimum lies somewhere depending on what those conditions are and how you drive your vehicle. That's all from me. If you are interested in some of this work in more detail, there are a few publications that I will leave on the screen so you can see. There is this model paper here, but it's old one, and we're about to submit the updated model, which is the results I showed you sometime soon. So if you're interested, drop me an email. I can send you that in due course. That's all for me. Thank you very much.
Fantastic. Thank you very much, Amir. Okay, so we'll now move to Alexander's presentation. So let me welcome him on stage. Thanks everyone for the questions. We'll be taking those after Alexander's presentation. And I just want to say for anyone who's having any kind of connectivity issues, you will receive an email with a replay of the event. After the event's over, you'll be able to review and catch up on anything that you've missed. Okay. Okay, Alexander, do you want to go ahead and put your slides up? Just notice you're still muted as well. Sorry, Amir, we'll just remove you from the stage for now. We'll welcome you back to answer those questions afterwards.
Thank you so much. Can you hear me okay?
Yes, coming through loud and clear. Take it away.
That's brilliant. Thank you all so much for coming. I'm Alexander McLaren. I'm an R&D engineer at PCS Instruments. So I work in research and development. But I also did my PhD at the Tribology group at Imperial College London with Amir for 4 years. So that is the link. My PhD was on electric vehicle transmission efficiency and reliability. And as Amir has aptly pointed out, there are several significant challenges in the design and optimization of both EV fluids and electric drive units in EVs themselves. And these create a perfect storm for tribologists because we have high-speed bearings that are electrified potentially by stray magnetic fields. And so understanding how these work and how the lubricants behave for them is challenged. Equally, we have very high contact pressures, for instance, in the low-speed stage of a gear reducer. We have high cycle components that potentially could fail by contact fatigue as a result of many, many contact cycles over lifetime. So, for instance, drive pinions. And we also have very high entrainment speeds, under which, as Amir said, the assumptions underlying classical EHL theory break down. As tribologists, it's really important to understand both these mechanisms, their effects, and the phenomena underlying them. But at present, they are difficult to model accurately. And so, as Amir said, experimental data is required. And PCS instruments are here to help with that. So the rigs that we design, make, and have supplied for years are applicable to all of these challenges. And so I'll just highlight a couple of these, and then I'll tell you a bit more about what PCS are up to at the moment, some exciting things in the pipeline, and also how we engage more widely with the community. So the MTM and MTM-EC, so that's mini traction machine electrical contact, or electrified contact, are just ball on disc tribometers. The ball and the disc are driven independently, and so you can achieve an arbitrary entrainment speed and slide roll ratio combination. They're loaded against each other to simulate really a bearing, the contact in a bearing. And this was one of the first machines that was able to measure friction in a single contact using materials and conditions that represented a bearing well. And so it's been instrumental in the development and of lubricants and the understanding of lubrication phenomena for several decades. Its younger brother, younger but much stronger brother, the ETM or extreme traction machine, which Amir mentioned briefly, can achieve contact pressures up to 7.1 gigapascals, obviously material dependent, in a circular contact. And it's the only machine that can achieve these pressures currently on the market. And so that's really good for understanding how lubricants behave under those conditions. The EHD high speed can achieve entrainment speeds of up to 20 meters a second, and similarly is able to measure film thickness in this quite extreme condition. And Amir showed some of my work during my PhD showing how strangely films can behave at high speeds as a result of the thermal coupling. And finally, our fatigue tester, the MPR, or micropitting rig, is able to generate 1 million contact cycles per hour. And in applications where you might have 100 million contact cycles over lifetime or higher, this means that in an accelerated test, you can representatively simulate that condition in a realistic amount of time. So between them, these rigs provide a really important suite of techniques that allow us to develop the next generation e-fluids. And finally, our optical technique, the space layer imaging method, or SLIM, enables in situ imaging of both tribofilms and elastohydrodynamic films. And so when they're behaving strangely as a result of electrical contact or as a result of starvation at very, very high speeds, you can optically see what's going on and then start understanding those mechanisms and optimizing those lubricants. I'm just going to briefly show you one example, combining some of those techniques. So this is the MTM-EC, like Amir showed, and a test that you might do, for instance, Amir showed that there's an effect on wear. I'm going to show there's an effect on tribofilm thickness. So here I've used SLIM to measure the tribofilm at different times during a test where we've rubbed two specimens against each other in the presence of a lubricant that contains an additive that forms a thick anti-wear film. So the non-electrified contact creates really quite thick films, while the electrified contact creates much thinner films under equivalent conditions. And this is perhaps one of the important things to know when you are designing a system where the contact might be electrified by stray fields. So who actually are PCS Instruments? We are a company that makes tribology lab equipment, specifically instruments for testing fuels and lubricants, and a few other things as well. We are just over 30 years old, and we span out of the Tribology group at Imperial College London, but since have really created ourselves a firm foundation in the tribology community worldwide. There are many hundreds of papers, academic papers written using our equipment, and increasingly industrial research and development, including in electric drive unit and electric drive fluid optimization, uses our rigs too. We are very active in the tribology community, and there's lots of exciting work that goes on. Some of our client stories are online, and these are all really exciting people with inspiring careers who have used our rigs and been kind enough to share how. There's also the Tribology Talks podcast, which you can check out on your favorite streaming service. Obviously, the hottest people currently in tribology are on there, myself included. And then you should also check out our newsletter and our insights articles online, all of which are opportunities for you to be edified tribologically. And we're quite active on LinkedIn as well. I'm not in the team that works on our LinkedIn content, so I can unbiased say that it's really engaging stuff, and you should definitely keep an eye on it. We also, and this is just a gift from us to you, have an app that acts as a quick Hertz contact calculator. So download now from your nearest app store, and the app allows the Hertz contact calculation at the touch of a button, easily for any PCS rig and combination of specimens that you could dream of, but also for an arbitrary contact, so you can apply it to any application you so wish. We are really anxious to understand what our customers are doing, and we would love to hear from you about the applications that you think are exciting. We'd like to know what you want to work on in the future and how we could help with that. There are lots of exciting things in the pipeline at PCS, so definitely watch this space. But in the meantime, have your say, get in touch with us, tell us what you're interested in. And so answer the poll questions in the poll tab, just to the right of this slide. But also let us know in the chat what you think, let us know how we could help you, and get in touch directly via our website. Give us a call, use the contact us form. We're always happy to hear from you, even if you just have an idea or a question, or you need technical support with one of our products at the moment. We have expertise broadly in the EV tribology field and more widely in tribology. Everything from ultra-high shear rate viscometry to micropitting and rolling contact fatigue to the testing of chocolate and wine and toothpaste, and lots of things in between. And our suite of rigs is used very widely by the tribology community, as I've said already. So I'll leave you with that. I've been Alexander McLaren, and thank you so much for attending this webinar. We really appreciate it, and we hope that you found it helpful.
Thank you very much, Alexander. It was a great presentation. Yeah, great highlights about the app. I've used it before, and it's pretty useful. But yeah,
I'm glad you found that. Yeah, I use it all the time. It's just like a quick thing to use. If you have any questions, I'll remain on stage, and also my colleagues are here to help as well.
Absolutely. So yeah, so we'll now take, as pointed out, so now we are almost at our 60-minute time, but as long as everyone else doesn't mind staying on for a few more minutes, we'll answer our questions. Welcome back to the stage, Amir.
Thank you.
Okay, so we did have one earlier from Gopal, who said, will there be any new oil analysis techniques for EV e-fluids, or would this be the same as the conventional one? I would like to point out Ben did add some answer in the chat. Yes, we absolutely do need new test standards and methods for EV to address the very tribological challenges involved, as mentioned in Dr. Kadirish's talk, e.g. copper compatibility, influence of electrical potentials, and higher speeds. Would either of you like to expand on that a little more, or anything in particular you want to highlight for new standards or test methods?
I think I tried to illustrate the challenges in terms of testing the tribological response of those fluids. I think this question is specifically relating to chemical analysis. That's how I read it. And I think a lot of the current existing tools can be used for that. Yes, the formulations ought to be slightly different, but I think we've got plenty of tools out there that can be used at the moment. I think the bigger challenge is really the tribometers. It's the speeds, the conditions, and so on.
Equally, scuffing, for instance, is something very difficult to test, but extremely relevant in electric vehicles. And currently, existing scuffing methods are either too time-consuming, expensive, and not sufficiently repeatable, or not very application representative. And so that's one area, for instance, in which there's room to develop a test method that is, much more EV applicable. And also, there are some tests that are not new in themselves, but have become much more relevant with EVs. So, for instance, foaming and thermal performance of fluids, which ultimately, depending on the design of your system, you'll have different application requirements. And so making sure that the test can give the OEM the information that they need about the fluid is something that is currently being done. And there are standards, but many of them just haven't really caught up with what we need yet. And that is currently happening. People are actively working on it. I think also those standard tests might get slightly more tailor-made to this application in the future. So all exciting things to watch happen.
Okay, thank you very much. Before we move on to the next question, I'd just like to release the attendance certificate. So if anyone wants that, please go ahead and click on that link. We're not stopping yet, but if you want it, click on that and then generate your attendance certificate after the event. We have our next question from Shirish, who asks, with EV systems operating at higher speeds, how do you foresee these challenges extending to valve train components in hybrid systems that might share characteristics with both internal combustion engines and EV systems? Whoever would like to answer first.
Shall I go? It's a balance, isn't it? You have to balance the chemical and the rheological and the mechanical properties of the fluid, and ultimately the formulation has to be application specific. So although previously when something like Dextron 6 or Mercon 5 was developed and we went, let's suddenly there's this ATF fluid that will work quite well for almost all systems that have this architecture in common. That is no longer yet the case for EVs. That no longer yet thing is like, we did this before, let's see if we can do it again. And what that requires is the designs to start solidifying to something that have something in common. And you have everything from high-speed epicyclic gearboxes in some EVs to change gearboxes with helical reducers and clutches and wet clutches potentially in other EVs, and those are two very, very different systems, and ultimately the optimal fluid for them is of course different as well. So valve train is just one of many challenges these fluids must meet.
Yeah, I mean you do have the advantage in a hybrid system of being able to use two fluids, what you put in your engine and what you put in the rest of the system doesn't have to be the same lubricant. But there are some specific challenges there that are not necessarily related to what we talked about here. So there have been increasing reports of fretting and false Brinelling damage, for example, in hybrid system, because you have two powertrains and usually one is operating, one is not doing nothing, and is shaking the other one. So fretting becomes an issue. There are issues with the oil temperature of the internal combustion engine in a hybrid system not being as expected in a pure ICE vehicle. And that does have an implication in terms of oil aging and the water content and so on. So I think the challenges it's different, if you like, but you do have this benefit of trying to optimize the oil for internal combustion engine and the oil for the system rather than sticking the same oil in it.
Okay, thank you. Got a question from Hausa here. It says, thank you, Dr. Amir, for this presentation. I wanted to ask how significant are shaft seal losses in EDUs?
I don't think it's any different from any other system, if you like. I don't have the numbers exactly as in separately for EDU, so I can't give you a value. But I think in general, the shaft seals, when used, if used, there are different designs, are significant at lower speeds. When you go in relative terms, when you go to high speeds, it tends to be the bearing drag, because seals are usually bearing. It's usually bearing drag in relative terms as the most important, and the contribution of seals reduces. You can see the published numbers from the model that I've showed you, which does have separate seal losses there, and you see exactly what I'm saying, that in relative terms, significantly lower speeds and then less significant at high speeds in relative terms.
Okay. Thank you. A question from Ray here. Who says, great presentation. Amir, you mentioned that your MTM EC tests used a low voltage of 5 volts and you were seeing some damage. Apart from voltage, amps play a role here too. Could you please provide some information on what amps or what current was used?
Yes, I can. To be honest, that single slide I showed you doesn't do justice to that work. We're about to submit the paper. It's an extremely complex area. You have this interaction between the effect of voltage on the boundary tribal layer film formation, and that subsequently has an effect on wear. But you also have the voltage or current, as you say, having an effect on damage itself. So it's a very complex system, particularly if you're looking at mixed lubrication conditions, which is what we are doing. When you're in full film conditions, things are a little bit simpler because it's a discharge, very high current density that does the damage. But you are right. It is both voltage and current. So in our tests, the voltage was 5 volts. In the results I showed you, we've also done tests at lower voltages, 1 volt, 2 volts. We've done loads of different voltages, but we are staying low. The current, because of the system, again, we didn't have time to talk about it, we can control the current, the maximum current, if you like. And that's in those tests controlled at 10 milliamps, the results I showed you. But that will depend on what the resistors are in your system and how you arrange your system. And you also have to remember that none of this is fixed throughout the test, because the voltages and current that I'm telling you are the start of the test. So you have ball and disc not contacting each other. There's a delta V of 5 volts across them. As soon as they contact, there's current flowing. We limit that current by having some resistor somewhere to 10 milliamps. What happens subsequent to that, we have no control over, because you're starting to develop a boundary film, which has electrical properties of its own. So the relation between the voltage and current of the contact and the system is then affected by that. But in our test, it's 10 milliamps. So we're trying to limit it to very low currents. So the damage we are seeing is not the damage as you may conventionally associate with high current discharge, if you like, in melting locally.
Okay. Thank you very much. We have a question here from Mshukter. Apologies if I'm pronouncing that incorrectly. So thank you, Dr. Omer, for the presentation. Is there any relationship with the gear material in use? I wonder if he's talking about material properties, mechanical properties of gears.
I mean, briefly, I mean, of course, material is important. I think in terms of restricting ourselves to what I talked about, which is efficiency, provided your gears are operating as gears, the effect on efficiency is limited. There are certain effects we know, and we published some work on this in terms of gear materials affecting the tribal layer film development, and that will have an effect on friction and hence on overall losses. You could argue that you can affect the thermal properties of the gear material and so on, but within the constraints we are working at, remember, gear materials do have to have certain properties in order to carry the stresses we are putting through them. I think the effect of materials on efficiency is limited. However, the effect on reliability is huge. It's if you want to make a step change in terms of reliability, you're probably talking about materials. So it depends on which aspect of those two things you are looking at.
Okay, thank you very much. We've got our final two questions. Another from Sharish, excuse me, who asks, do you think there's a need for an update? Sorry, I'll begin again. Do you think there's a need for updated test standards for tribological performance specific to hybrid engine valve trains to align with the standards evolving for EV components?
I think I'll let PCS answer that. We don't do much with standards. Sorry, Alex.
I don't have a lot to add other than that obviously in valve trains, the contacts have their own requirements. There are many other components that the fluid might also see. I mean, Amir made the point just now that it would be slightly odd if the engine were lubricated by exactly the same fluid as the transmission. And indeed, perhaps those requirements could be balanced for that component with the engine fluid rather than with the transmission fluid. But the hybrid space is something that obviously is even broader in terms of the different combinations that you might have and the different requirements you might put on the lubricant. And so although there are standards involved for testing certain performance parameters on EV fluids, I think it will be a very long time before we have a standard that says this is the perfect fluid for an electric vehicle, because it's not currently reasonable to expect such a fluid to exist, given that every electric vehicle has very different requirements. Perhaps the optimization will over many years converge on a particular design, but at the moment we're in the exciting scenario where there are lots of different things going on, and we get to see all of them happening at once.
Absolutely, yes. What a very exciting time indeed. And now on to our final question from Rohit, who asks, how do you think the unpredictable initiation of electrical discharge damage can influence gears and bearings high cycle fatigue life? And then I think there's one here specifically for PCS. Is the MPR rig being developed to apply electrical potential?
I will jump in here and say that the MPR rig has been used to apply electric potential by several research groups, including Argonne National Labs in America, and also Monica Ratoya's group in the UK. So there are many people already, and at Imperial actually, I should add. There are many people who have done this. Obviously, the phenomenon is quite complex. Ultimately, contact fatigue happens as a result of cyclic asperity stresses in the case of micropitting, and other contact stresses, which then allow cracks to propagate. If you damage the surface electrically, many things could happen to both the microstructure and the surface, which then change the way those stresses are affected over lifetime, and ultimately change the nature of the crack significantly. So, for instance, there's this new term EWECS, as in electrically induced white etching cracks, which has extended the study of white etching cracks in other situations. It's just one of many examples of quite complicated damage mechanisms that might be induced, and the MPR is an ideal instrument to study that. You should definitely buy one, and you should definitely use it in an electrified case. There may also in the future be more provision in the same way that the MTMEC has been updated in the MPR for that off the shelf, but at the moment it's a modification that can be done by the customer.
Okay, great, thank you. Yeah, that certainly sounds like it'd be one of those areas where there are so many variables and so many things that could change during that test. You would have to be very careful in setup, and yeah.
Yeah, I keep fairly quiet about my own experience of studying fatigue. It was an interesting exercise, and yeah, everybody who's done it knows what I mean.
Yeah, I think we've all had those. I think every tribologist at some point ventures into looking at fatigue and then goes like, "Oh my goodness, what is this?" But yes, I think with that, before we veer off into other discussions, we are all out of questions. We are slightly over time, so thank you to both of you for staying to answer those for those questions. Thank you to everyone in the audience that stayed to listen. And I think this is now a good time to bring the webinar to a close. So with that, thank you very much, Emir. Fantastic presentation, giving us lots to think about. Yep, I'll certainly need to be doing some reading later in order to explore the topic further. Thank you very much, Alexander, for that great presentation for PCS Instruments. Thank you to PCS Instruments for the support for this event. We wouldn't be able to do what we do without our partners. As a reminder, if you're interested in other offerings from Surface Ventures, please do visit our website. You can see our upcoming events, which we've got Professor Guo on the 30th of January, who will be speaking on biomimetic surfaces. So please do keep an eye out for that. We'll be updating with further information once we have it. Also, do look at our LinkedIn page. Our newsletter is there, releasing fortnightly, the next one coming next week. And as a final message, if you have enjoyed this, know of any friends or colleagues that this would benefit, please do tell them about these webinars. It would be great for us to continue to grow our audience and keep bringing you great speakers like we had here today. So with that, thank you very much, everyone, and have a good rest of your day.
Thank you. Bye.
Thank you.
Thanks. Bye, everyone.